So yeah, I'll be talking about polar codes. So the general setting that we'll deal with is the familiar setting of channel coding, in which we have a message that we want to transmit over a noisy channel. And we use error correcting codes to encode a message into a larger space. OK, so kind of the fundamental theorem is Shannon's theorem, which tells us that for any discrete memoryless channel, there's an associated constant known as the channel capacity, such that we can communicate at any rate that's below the capacity. And conversely, for any rate that is above the capacity, we have to incur some probability of miscommunication. So suppose we have a rate r that is epsilon less than the capacity. We're going to say that the gap to capacity is epsilon. So this is the terminology we will be using. And the challenge that coding theorists care about is actually finding error correcting codes that achieve arbitrarily small gap to capacity. OK, so just to kind of set the bar, if we take random codes, it turns out that Shannon's theorem shows us if we want a gap of roughly epsilon, it suffices to take a random code of block length n, which scales quadratically in 1 over the gap. But of course, we want to know actual explicit codes that achieve capacity. So that will sort of be the guiding question for the remainder of the talk. So let's just formalize the problem. So we're given a discrete memoryless channel W, and we're given a parameter epsilon, which is the gap to capacity that we want to target. So the problem is as follows. We want to construct an explicit error correcting code with an encoding and decoding map that is explicit, such that the rate is within epsilon of capacity. We also want the block length to scale polynomially in 1 over the gap. So this is kind of the focus of what we're going to prove later on. We also want our code to be efficient, so I should be able to compute the encoding and decoding functions in time that is also polynomial. And finally, we want the communication scheme to be reliable, so the probability of miscommunication should go to 0 asymptotically. OK, so before we talk about the contribution of this work, let's just look at some of the codes that are out there that either achieve capacity or get close to capacity. So sort of the classic example is concatenated codes, which are known to achieve arbitrarily small gap to capacity. Unfortunately, the decoding complexity for the range of parameters that we care about scales exponentially in 1 over the gap squared. So this is not very practical for achieving capacity. We also have LDPC codes, which are widely used, but we only know that they approach capacity for the erasure channel. Turbo codes also are widely used in practice, but again, we don't have any theoretical results that show arbitrarily closeness to capacity. There's been some recent work with spatially coupled LDPC codes, and these are actually known to achieve capacity with arbitrarily small gap, but there's still questions about how the block length scales. And finally, the focus of our talk will be polar codes, which are known to achieve capacity for symmetric channels. OK, so I just want to state that polar codes are the first known construction, at least explicit construction, that achieves capacity with the guarantees that we listed in the slide on the problem formulation. So in particular, the rate gets arbitrarily close to capacity. The encoder and decoder complexity is n log n, which is polynomial in the block length. And for polar codes over binary alphabets, there are a couple of works that show how fast we get a convergence to capacity. In particular, there's some constancy such that it suffices to take a block length of 1 over epsilon to the c.
So, how about the expanded codes? They too do that, right?
So expander codes, yeah, I mean, there's some question about like if you want to achieve close to capacity, how that works. We can take it offline.
I don't think they do, because you still need some, I mean, the constructions, they give you some error correcting radius, but they don't shit. And if you do any concatenation, then the inequality is still there's still exponential complexity.
Yeah, it's even the 1 and epsilon squared, just like
No, but they're constant size Unicodes.
No,
but to get close to capacity, the
but
constant
you
goes
measure
up.
it is not in terms of the block length, you measure this in terms of the gap to capacity.
Oh, I see.
Right. So even for concatenated codes, the general setting, the decoding time is fast. But for the range of parameters we want to get close to capacity, the scaling is exponential. Okay, so the question we want to ask is, what about polar codes over non-binary alphabets? So the main contribution of this work is to extend the work of Guruswamy Shah, which deals with binary codes, to q-ary polar codes for prime q. So in particular, we show that the rate to get an epsilon gap to capacity, it suffices to take Blanc-Levenpet's polynomial. The only difference this time is that the constant we get is dependent on q. Okay, so as a consequence, these are the first explicitly efficiently encodable, decodable codes that we know. And as far as I know, the only construction that we know so far with the theoretical guarantees for speed of convergence.
Can I ask a quick question?
Yeah, go.
How does C go as Q gets bigger?
So right now in our analysis, it's polynomial in Q. So it's, for those of you who care about the practical considerations, it's quite bad. But that's part of our analysis. It's quite possible that the constant should not depend on Q, but we don't know that at the moment. And the sort of technical ingredient that we use to establish our theorem is an entropic increase inequality over prime alphabets. So the original analysis for analyzing the convergence to capacity used martingale convergence theorems. And so we bypassed this with a entropic increase inequality. So I'll talk a bit about that later in the talk. So I should just say that in the work of Guruswamy Shah, the entropic increase inequality was implicit in their work. But for higher Q, there's actually some technical difficulties that arise. So it's not really a simple extension of the Q equals 2 case. Again, I'll touch on this later. Okay, so let's just kind of recall how polar codes work. So there have been a couple of talks during this workshop which describe the construction and how to decode polar codes. We won't really have time to talk about that in detail, but let's just go over sort of the main points you need to know. So first of all, I want to restrict our attention to symmetric discrete memberless channels W. And I'll find it convenient to talk about, to think of channels as kind of correlated random variables X and Y, where you can think of X as the input of the channel and Y as the output. And again, we'll be dealing with channels where the input X is supported on an alphabet size of Q. So I'm going to define this notation H of W for channel W to be simply the conditional entropy of the input X given Y. And assuming that, so because this is a symmetric channel, assuming that X is uniform on its input, this is equal to 1 minus the channel capacity. So one note that I want to make is that the entropies that we're going to work with are actually normalized. So recall that our variables are on an alphabet of size Q. So entropies are distributed between 0 and log Q. So we're going to actually normalize by log Q because we want the entropies to lie between 0 and 1. So for the remainder of the talk, just assume that whenever I use H, it's actually normalized by log Q. So is there any question about that? Okay, so the setup is as follows. We're going to take n copies of our input X, denoted X0 through Xn minus 1. And we're going to run this through basically n instances of our channel W. And we get output y naught through yn minus 1. And now the idea is that we have some polarizing matrix Pn, which takes our x's to u's. Right, and the thing to note is that the conditional entropy of the u's given the y's is precisely the entropy of the x's given the y's. And this is simply because we have an invertible map that goes between the two. And this is also the entropy of the channel times the number of copies we have. Okay, so we're going to define these intermediate channels. So remember, we've taken n copies of W, and we're going to split this into n new channels that we denote W0 through Wn minus 1. And the ith channel is basically going to be, you can look at it as taking input ui and outputting the previous u's as well as all the outputs of the channel. So these are our new channels. And it's not too hard to see that by the chain rule for entropies, if we add the entropies of these channels, it's going to be equal to the total for the n copies of W that we started with. So we're preserving the sum of the entropies. Okay, so I've just kind of formulated that on the next slide. So the main property that we want from our map P of n is that as n goes to infinity, we want all of these h values to go to either 0 or 1. So if we have any interval that's sort of in the middle, there should be a vanishing probability that one of these lies in the middle. So that's the property we want. And then, as you may recall, so once we have n large enough, we have the set of channels whose entropy is close to 0 and the ones close to 1. And since we know what the total entropy is, we know that roughly the fraction of channels that are close to 0 will be close to the channel capacity of W, the normalized channel capacity. So our code can, so we've taken n copies of W, and we've split them into channels which are all either close to perfect channels or close to completely useless channels. And we use the channels that are close to perfect. Okay, so let's just take an example for 2x2 matrices. So again, we have a channel W over a q-ary input. And let's look at the following map, which is the original map that Archon considered. So if u0 is the sum of x0 and x1, and u1 is the sum of x1, this is going to achieve polarization, which I'll describe. So in particular, if we take two copies x0, y0 and x1, y1, we can take two copies of our channel and split them into W minus and W plus. And I guess these are the only equations that we need to know. So if we sum the entropies of W minus and W plus, that preserves what we started with. But on the other hand, we get a split between the channels that we have obtained. Okay, so using this G2 matrix, we can kind of recursively do this for increasing block lengths n. So we just kind of, if we have n equals 2 to the little n, then we can kind of do little n layers of this, this 2x2 matrix. So I'm not going to go into too many details, but basically what we need to know is we need a handle on the channels that we obtain after splitting n copies of W. And what we need to know is that, okay, so in the 2x2 case, we started with two copies of W, and we constructed W minus and W plus. So that's sort of going down one step in this tree. Now what I can do is kind of repeat this with the W minus and W plus channels. So if we go down another layer, we get 4 channels, and we can continue this for little n steps. So at the leaf, we get 2 to the n channels. And so these are going to be precisely the channels that we obtain after using the polarizing matrix. So are there any questions on that so far?
What's the rate and the decoding probability that you get as a function of capacity for the binary case?
For the binary case, the decoding probability is roughly exponential in negative square root of the block length.
As a function of gap to
And n is 1 over epsilon to the, well, the actual constant we don't know, but you can get something around 4.
it's just poly 1 over epsilon.
Right. Okay, so we have this tree of channels, and remember the channels of interest are the ones at the bottom level. And our goal is to show that all of these channels are close to 0 or 1 in entropy value. Okay, so the initial analysis that was used some years ago was the use of martingale convergence theorems. So if we, in particular, you can think of a random walk, which starts at the top node. And at each step, we either go to the left or to the right with probability half. So we go W minus or W plus, each with probability half. And you can think of just going for n steps until you reach the bottom. So for the jth level, we can consider the random variable, which tells you the entropy. So if hj is the entropy at the jth level, the sequence of h naught, h1 forms a martingale. And moreover, the martingale is bounded. And we can also consider the fixed points of evolution. So in particular, for 0 and 1, the channel evolution is fixed. This corresponds to W being either a perfect channel or a completely useless channel. So in particular, the martingale convergence theorem tells us that we converge to a 0, 1 valued random variable. And this gives us the convergence to capacity. Unfortunately, the fact that we use martingale convergence means that we know nothing about the speed of convergence. So to sort of get guarantees on the block length, we need some other analysis technique that avoids martingales. So our solution is to argue directly about the entropies of these channels as we go down the tree. Okay, so the key technical ingredient that saves us from the appeal to martingales is this entropic inequality. So again, channel is going to be W with, you can think of input X and output Y. So what we really want to do is quantify how much the channel splits when we go to W minus and W plus. So remember, we start, one level of the evolution, we start with 2 copies of W, and we split into W minus and W plus. And we want to know how much does W minus actually deviate from W. And it turns out that what we need is a linear increase in H times 1 minus H. So you can kind of unroll the definition of these H of W's and H of W minuses. And the theorem we need is basically that if we have these correlated random variables where X is supported on an alphabet of size Q, we can take 2 independent copies and we get the following inequality. So just to kind of give you an idea of what was known, this inequality was known with the right-hand side being a quadratic term. However, this is not sufficient to get a block length which is polynomial. So we really need a linear increase. Okay, so before I talk about the entropic inequality, I just want to say why does this give us the convergence result that we need? So in particular, the entropic inequality allows us to argue as follows. So if we take a look at a channel W, we look at h of W times 1 minus h of W and look at the square root of that. What we can argue is that each time we go down one level of the tree, the expected value of this goes down by a constant factor. So in particular, what that tells us is that if we go for roughly log of 1 over epsilon recursive steps, the probability that you have an entropy that's close to 0 will be roughly I of W, the normalized channel capacity. Okay, so this we call rough polarization. We've shown that for roughly log of 1 over epsilon steps, we end up with roughly I of W entropies that are close to 0. But unfortunately, this is not good enough for us. We actually need to show that these entropies are not just less than epsilon, but actually much less than 1 over the block length. And the reason we need this is that these h of n's actually, when we're doing the decoding process, they give us an estimate of the probability that we decode a bit incorrectly. So in the end, if we want to argue that the decoding probability is low, we need to do a union bound over close to n items. So to survive the union bound, we need a fraction that's much less than 1 over n. So the idea is that you can kind of do this rough polarization. So I've denoted the entropies that are smaller than epsilon in green. So these are your good entropies. And the ones that are bigger are red. So these are the bad ones. And the idea is that we completely give up on the bad nodes. And starting from one of these good nodes, we can drive down the entropies even faster. So I'm not going to show you the details, but it turns out that if you sort of start from one of these nodes, then most of the paths are actually good and will polarize fairly quickly. And we analyze the decrease of the entropy using something called the Bhattacharya parameter. This is basically an estimate of, it's a parameter that allows us to estimate the entropy, you can think of it as. Dealing with the entropies directly is kind of difficult, so we use this kind of as a proxy to analyze the entropies. So I'm not going to go through the details, but you can just trust me on this one. Okay, so now let's go back to the entropy inequality now that I've hopefully convinced you that this is the key item that we need. So for the binary case, the inequality is as follows. And it turns out that if we fix this conditional entropy x given y, we have a very simple characterization for what minimizes the left-hand side. So in particular, it turns out that the sort of minimum distribution for the left-hand side happens when each of these conditional entropies, when you fix a particular y, are equal. And what this effectively does for us is allows us to remove all these conditional entropies and just argue about unconditional entropies. So really, we just need this simple inequality for unconditional binary random variables. And since it's a binary variable, the entropy is characterized completely by, say, the weight on a particular element, say 0. So we can actually just explicitly compute this, and it's quite easy to show. So how am I doing that then? Okay. So the problem with the q-ary case is that we don't know any easy characterization for this extremal case. So here, really, the extremal case told us that we can pass to an unconditional inequality, but for the q-ary case, this characterization seems false. So this makes the q-ary case much harder. So I'm going to skip through this. It's kind of technical. Okay, so now I've shown you that, so I haven't gone through the proof, but it's kind of technical, but we established the inequality for prime q. So you may wonder the question, what about non-prime q? So why do we need primality of q? So it turns out that in general, this inequality is not true. And in fact, polarization itself does not hold for non-prime q. And the reason is that suppose x is a random variable on q elements. If q is not prime, then we have an additive subgroup of 0, 1 through q. And basically, I can take a counterexample in which x is supported on a subgroup. So if I take 2 copies of x and add them, we will always stay inside the subgroup. So if x is uniform on the subgroup, then we're basically not going to get any increase on the left side. So this is kind of the reason that you cannot expect something like this to hold for non-prime q. However, you can still construct capacity achieving codes for non-prime q. And what you can kind of do is factor q into primes, and you can take polar codes over these prime alphabets and kind of piece them together. So this is what we call multi-level code construction, and this has appeared in a couple of papers. And then you can do a similar successive cancellation decoding, which I'm not going to go through for this talk. Okay, so conclusion. Polar codes have polynomial gap to capacity for alphabets of prime size. And we can also use these to construct codes for non-prime alphabets. And it should be noted, I didn't really talk about source coding, but the construction we have works for source coding as well. So that's lossless data compression. So the main open question that I see is pinning down this optimal value of c. So I mentioned in response to the earlier question that in our analysis, c is dependent on the prime q. However, what is the true constant c? In particular, as q goes to infinity, can we show that c approaches 2, which is kind of the constant you get from random coding? And then there's also the entropic inequality, which is of independent interest. And you can pin down what the linear increase factor is in the entropic inequality. Unfortunately, it's not too hard to show that you cannot get a constant that's better than 1 over log q. So in particular, if you're trying to show a constant c here, which is, maybe, approaches a constant as q goes to infinity, this is not going to be possible with our entropic inequality approach because simply we get a bad dependence on alpha. And alpha currently is polynomial in q, but okay. And finally, I should just mention that the entropic inequality, you can view it as a entropic version of a sum set inequality. So in additive combinatorics, there are a number of inequalities of the flavor where you have a particular set, and you have some additive structure, and you add it to itself, and you want to kind of analyze how much it grows. So here, the entropic analog is you have a random variable with certain entropy, and then you sort of take 2 copies, add them together, and analyze the entropy. So really, you can view this as a sum set inequality in the entropy setting. So there's a lot of connections there to explore, which I have not really dealt with so far. And then finally, the question of, we dealt with this particular polarizing map, the 1101 matrix. What can you say for other polarizing maps? Do you still get the polynomial convergence? So that would be interesting to see. And that's all I have for today. Thanks.
Why do you say it doesn't work for lossy source coding? It does work for lossy source coding, right? Coded code.
Sure.
I say it only lossless source code.
Yeah, I mean you can do it for lossy as well.
Yes.
So, are you just using the polarizing map where the matrix is the 1, 1, 1 matrix, right?
Right.
This thing for Q, it seems like if you wanted to have a different dependence on Q, you might change that matrix. So each time you're only adding, so it's going to take a long time to mix things, right? If you multiply by 2, then you might see a much faster mixing.
So if the coefficients are...
Like 1, 2, 1 kind of thing.
Yeah, I mean, I think that would be interesting to see what happens for other maps. But ultimately, you would need some kind of entropic inequality that deals with coefficients.
In the case when Q is the power of a prime, let's say 8, it has an additive subgroup.
Right.
Is it clear that there is no polarizing map which will give you the required inequality?
So if you just consider linear maps, you're going to run into the same problem. It's not just the 1101 map. So you really, for prime powers, you need some kind of non-linearity. So there's some work that...
Just pick a primitive element. Isn't there work on polarizing thing for GF for a prime power? Should you pick a primitive element?
It won't, but you can change what is my polarization. That's easier. If you don't insist that you get perfect versus junk, you just get easy, then everything works. Even with these subgroups and so on and so forth. Even with the usual stuff.
I'll look at it back.
It's the same as a subgroup structure. I mean, things will work, but not in the polarization as we find here.
So there is a work, I believe, Teletar is on it, in which you can look at a similar map as the 1101, but instead of U1 equal to X1, you can do some kind of permutation of the distribution of X1. So you can think of X as having different weights on your Q elements, and you can kind of permute them. So that's a nonlinear step. But in general, you need some kind of nonlinearity.
I have a naive question.
Yeah.
Is 2 the best you could possibly get, even with big Q?
Yes. That's... I mean, so I don't know of a lower bound for this particular inequality.
That comes from general.
That's just from the Shannon. Yeah, but it's important to note that we don't... so for Q equals 2, we know a lower bound on C, which is roughly 3.5, I think. But for general Q, I'm not aware of any lower bound in this argument. But the general C equals 2 follows from just general principles of Shannon.
The C goes up as Q goes up, is that right?
Right. In our particular analysis, we show this for an increasing function, but that might just be an artifact of our analysis.
Maybe not.
So in particular, maybe if Q increases enough, you start to decrease.
Okay. Good. Thank you very much.